Hello everybody and welcome. I hope you're having a great virtual JNUC event. My name is Jaron Bradley and I am the detections lead here at Jamf Protect. Today we're going to talk about incident response with Jamf. This is going to be everything from getting an alert to performing analysis on that alert and confirming it's malicious, all the way through the incident response steps, ultimately ending with remediation and cleanup. So this is a lot to cover in a 30-minute session, so let's go ahead and dive in. So let's say that we have a detection come in called plist disguised as Apple. For those of you that have been to my talks in previous years or other talks this year, you've probably heard me reference this detection. It is one of my absolute favorites. It looks for any time a launch daemon or launch agent is created that uses the prefix com.apple. However, the executable that it's trying to run at startup is not signed by Apple. In other words, we're looking for persistence items that try to run new processes when the system starts up, where the file name implies it's an Apple process, but the file executing is not actually Apple's. This is done by a lot of malware, numerous samples out there. Com.apple is often used to try and blend in with the operating system so that you won't think anything of those files if you happen to come across them. In this case, we see that the name of the launch agent being created is com.apple.systemupdate.plist. However, if we look inside this file and we see what it's trying to run at startup, we see that it's trying to run something called update.sh, which is a shell script. It can't even be signed. Apple is not really in the habit of creating such launch items. Apple's almost always going to use a binary somewhere rather than a shell script. You can't even sign a shell script. So there's so many red flags here that it's very suspicious right off the bat just looking at this. Another red flag would be the fact that this is an executable, update.sh, is an executable sitting inside the user's library directory. The user's library directory is generally used to hold a bunch more files. It's not really used to hold executables all that much. So there's a lot of different red flags here. If we go down to the bottom, we get the file system event details, and we can actually see the location of this plist is inside of the user's library launch agents directory. So this is just a launch agent. It runs with the user's permissions, and it will be loaded at startup. Finally, we can also see the process that created this launch agent, and we see that it's called System Updater sitting inside of a very strange directory. Now, if you're not familiar with the app translocation directory, this directory is actually created by the operating system the first time you open an application. So we know that this is the first time the System Updater application is being opened. And the reason this strange directory is created is so Apple can identify it, and so that Apple can move this application to that directory and then throw a number of prompts on the screen saying, hey, this is the first time you're opening this app. It was downloaded from the internet. Are you sure you want to open it? And other prompts like that. Meanwhile, it's sitting in this protected directory so that it can't be modified while the user is answering these prompts. Now in the Jamf Protect UI, if we move into the Processes tab, we get additional information on the System Updater application. Remember, this is the application that created this suspicious plist we're so interested in. In the details, we can see that it's actually signed ad hoc. It's not actually signed by a developer. Nobody has really claimed it as a developer. Instead, in Xcode, for those of you who aren't familiar with the developer process, you kind of had the option to skip the signing process and sign it ad hoc for testing purposes generally. A lot of malware does not come signed. It is not uncommon to see that. But nowadays, it's getting so hard to run applications if the process or if the application isn't signed that we are starting to see a lot more signed malware. In this case, it's not signed, it's ad hoc, and the user will have to be much more intentional about running the application. They'll have to go around the gatekeeper prompts, they'll have to right click it, click open, so on and so forth. For simplicity purposes, we didn't want to sign this malware, even though it is just a demonstration. but we've instead disabled gatekeeper on the victim system. So we'll get in a bit more to that later, but for now, just note that this application is running and it's not signed by a developer, and that therefore also, once again, makes this very, very suspicious. So if we move over to the binaries tab, we can actually get a little more context about the executables at play here. The first is the system updater application that we've been looking so much into. We can look at this and we see that in the extended attributes, which are little metadata tags that get applied to some applications and some files, we actually see that this carries the com.apple.quarantine attribute. What this means is that this file in some manner was downloaded from the internet, whether that be through Safari, Google Chrome, some other browser, some chat mechanism. It came from the internet somehow, and therefore Apple tagged it with the com.apple.quarantine extended attribute. If we go down a little bit and look at the update.sh script that we don't know what it's doing, but we do know it's being run at startup, we see an extended attribute there as well. In this case, it's com.apple.text encoding. This doesn't really provide us with any new context because we know based on the file extension that this is a shell script. But for instance, if this file was just called update instead of update.sh, this extension or this extended attribute would tell us that this is some type of text file, and we could probably make the assumption that it's a script because it has executable permissions. So again, it doesn't provide a ton of extra context here, but in some cases, this little extended attribute could be cool to see. There's no guarantee that this extended attribute will exist on every text file. It depends on how that text file is created, but however it was created in this sense, it got applied automatically. Finally, we'll move into the Users tab. The Users tab just tells us the different users at play in the context of this detection. Here we see that it's a test user of UID 501. We don't see any signs that the root account was compromised, or at least not yet. And this is good. That definitely works in our favor. Having root does allow malware to bury deeper into the system. However, it's still very dangerous even without those root permissions. It's still able to steal files. It could still run ransomware. It's still able to sit there, wait, and hide unnoticed. But root would allow it to dig much, much deeper. So we're glad we don't see that at play yet. All right, so a quick review of what we know so far. First off, we have an application called systemupdater.app that was downloaded. That app is not signed by a developer. That application then went on to write a persistence item called com.apple.systemupdate.plist. This plist at startup will launch a script called update.sh that is just sitting inside of the library directory. Using a single alert, we've actually been able to figure out quite a few details, but there's a few things that we haven't quite pieced together yet. One is, where did this malware come from? And two, what is its goal, or what was the final payload that it's now running at startup? So we're going to further investigate these things. Now, one of the first things I'll do when investigating a scenario where I want more details is to check to see if any additional alerts or logs occurred on this system around the same time. The easiest way to do this in the Jamf Protect UI is by selecting the computer name you're interested in. Now keep in mind this is a test system, so the results are of course going to be a little skewed because it's not continually running and feeding data up. But a lot of times when triaging a specific system, you might be able to find a spike in logs and alerts when something suspicious occurred. Here on this system, we can see that when the suspicious plist detection occurred, it appears a handful of log events occurred as well. So we'll take a look at what happened here. Notice that at the same time we see this suspicious plist created, we also received a log event titled Safari writes a custom URL handler. This custom URL handler has the value of system update. Let's pause here for just a second to discuss why this is relevant to our investigation and what exactly a custom URL handler is and how it works. So let's break this down. A custom URL scheme is simply a way for one application to request that another application be opened, perhaps even with some additional data passed to it. Although it's being used maliciously in our scenario, it's not malicious in nature. Otherwise, Apple would not continue to support it. A good example of a custom URL scheme is the Microsoft Office suite. Using a crafted Office custom URL scheme, a user can request many different applications be opened in the Office suite, and even provide a link to a document that's hosted online somewhere. Using this single link, the specified application will be executed, and that application will download and open the document all in one go, instead of requiring a user to download the document and then open it separately. Ultimately, it's a way to pass data between apps in a more automated fashion, so that fewer clicks are required and less copying and pasting. Another good example of this is an app like Spotify that allows you to go copy a link and then share that link with a friend over text. So long as they have Spotify installed as well, when they click this Spotify custom URL link, it will open the song that you wanted them to hear inside of Spotify instead of trying to bring you to a website or something like that. So how's this look from an attacker perspective? Well, when you're building an application, in this case when the attacker built their application, they would define that custom URL scheme inside of their info.plist. This is just defined under URL schemes. So this is the string, this is the magic string that will now open this application from within another application on the system. That info.plist will continue to exist inside the application, obviously, and the attacker zips that file up. That file then, this zip file then gets hosted on the internet at some magic link. The reason it's a zip file in this case is because, remember, an application is just a structured directory. And if you're browsing the internet, you can't download a directory. You have to be downloading a file of some type. So zip's kind of perfect for this. It ensures that when you do download the application, you're getting the entire directory. So the attacker then convinces a user to visit the website, and that zip is downloaded. Not only is it downloaded, but if Safari notices a zip file with an application inside of it, it's automatically going to unzip it. It does this in the interest of keeping some automation and making it so apps can easily be downloaded, once again requiring a few less clicks because we get impatient and we hate clicking. So Safari goes ahead and automatically unzips that zip file. When the application hits the file system, one of these services on macOS notices there's a new app. It goes and looks at the info.plist and it registers the custom URL scheme inside of that plist. So now the website or the server is able to request that app be opened just using the scheme. Again, all this to save just a few clicks, actually just to save one click, and that's between when the user downloads the file and when it is on their dock. They no longer have to click it on their dock. Instead, the website can request that app be opened immediately. Now, there's still going to be some prompts, just like you saw with the Microsoft Office example. The user's still going to have to click through some stuff, and all the same terms of gatekeeper still apply here. But why does the attacker continue to do this anyway? Is because it's incredibly easy to define in their app, and if they can spare one extra click and increase the likelihood the app actually is going to be opened, they're going to do it if it's simple. All right, so at this point, we've used entirely the Jamf Protect UI to confirm this system is basically compromised. Now, what you might want to do also is you might want to get on this system and collect additional artifacts to aid you in your investigation, or just to confirm what you're seeing in the UI is the details in their entirety. So this will depend scenario to scenario and attack vector to attack vector. But in this case, we just kind of want to go collect the files and further investigate. So to do that, we're going to use Jamf Pro, and we're going to log in and go to the settings. Once we go to the settings, we're going to go down to scripts, and we're going to create a bash script that's going to run and collect the interesting artifacts that we want to pull back. It'll put them all in a zip file, and we'll push them up to our Jamf Pro. So I'll break down this script really quickly in terms of what we're going to collect. We're going to first go collect the malicious app that we're interested in and make sure maybe we can do some reverse engineering there later, Maybe we can do some investigation, just check out the strings, see if this is known malware, things like that. So we'll grab that app first, and then we will run a tool called TrueTree. I'll get into what this is coming up. And then we're going to go grab some of the artifacts just to help reconfirm what we're seeing. One of these is going to be the Safari history database, because we know Safari was definitely at play here. The Quarantines SQLite database, the LS Quarantine. This is one of my favorites. I'll get into that. We're going to grab the plist, the launch agent that is being dropped on this system. And then finally, we're going to grab the update.sh script that is being run at startup, because we still don't even know what's inside of that. Finally, we'll zip it all up into a single zip file, and then we'll use the Jamf Pro API to get this zip file up to our Jamf Pro instance, where we can then go see it inside this computer's attachments. And we can pull that zip file and then just start looking at all the files inside of it. So now we can go to our policies, and we can create a new policy, and we will just call this collection, because basically that's all it's being used for. We want to run this the next time this computer checks in with Jamf Pro. That's going to depend on what you have your check-in time set to, or your check-in frequency set to. But hopefully within a half hour it'll execute. So we need to make sure, go into the scripts, we'll add this as a script that runs with this policy, and then we should be good. The next time this computer checks in, we should be able to pull this zip file and start investigating. So if we go ahead and open up the Safari web browser history that we collected off the system, we notice something almost instantly inside the history items. And that is that the latest entry was an IP address that was visited, likely hosting a website on port 8000. This is very strange. Most attackers will use a domain nowadays. They'll buy a domain that blends in and doesn't really look suspicious. In this case, we see that the attacker just hosted something directly on a server using the IP address. Some attackers will still do this, but it's fairly uncommon. So this instantly kind of screams to us to investigate further. Now, this is the latest entry, and again, this is a test system. There are other ways that we could come to the conclusion that this particular entry is a suspicious one, and most of that would have to do with timeline analysis. We'd actually go through the history items and find out what time this website was visited, and the odds are that it's going to line up directly with the time that the detection occurred. Next, we'll go ahead and move into one of my favorite artifact items on macOS, and that is the LS Quarantine database. This is a SQLite database stored inside of the user's home directory and library preferences. Now, this database actually gives us a full record of what's been downloaded on this system from various different applications. It does matter how the application was designed as to whether or not it will end up in this database, but when it comes to all major web browsers, they are all talking to this database and recording information here. So what we actually see is we can actually see that Safari downloaded an item from this IP address that we have in question. And not only that, but we see that it has downloaded the system updater.zip. So if the Safari database, the Safari history database wasn't really enough to show us this, we have now completely confirmed using the LS Quarantine database. Now with the launch agent that we've collected, we don't really see a whole lot here we didn't already know. We see that the program set to run is update.sh, and we know that that's ultimately going to go on to create the Python backdoor. One thing we can learn by looking at the raw contents of this is that the keep alive value is set to true. The keep alive value is going to tell LaunchD to try and recreate this Python backdoor if it's ever killed. So immediately after seeing that it's dead, it's going to then run it again and try to call back to the attacker. This is not a super stealthy technique. It's fairly noisy. A lot of more stealthy operations might say sleep for, say, 5 minutes before trying to call back to the attacker again. But with the keep alive set to true, this is just going to keep retrying and retrying. One of the other items here we see that's kind of interesting is limit load session to type Aqua. Aqua is related to GUI applications. And we haven't really seen any signs that there's any of that involved here, which tells us that this launch daemon was very likely a copy and paste type job, implying that maybe we're dealing with an amateur attacker. This persistence item was just not super thought out. So finally we get to the update.sh script. This is the script that's running at startup that the launch agent is kicking off. And the first thing we'll notice is how interesting it looks. This is a very hacky looking Python command running from a bash script. So the python-c is going to execute Python code directly from the command line. So more signs that we're possibly dealing with an amateur attacker. They could have instead just created a Python script that made a reverse shell, but in this case they're calling bash to call Python, which is just kind of a weird approach. And a little amateur. So this code that they're running in Python is also kind of very pen testy, very easy to find online, copy and paste. So what you're actually seeing there is the IP address the user wants to connect to right in the middle. And then on port 8080 is what they'll be dialing back to. So this actually just gives the attacker a very basic shell where they're able to run pretty much any command that's on the operating system, so long as the user has permissions to those commands. So what they're going to do now is either just leave this hanging here, maybe they'll steal data, but I have seen basic shells like this used before in persistence. Generally the attacker might stick around for a while and decide to later drop a more sophisticated backdoor on the system, but sometimes just that initial connection to get a basic shell is done through commands like this. On any operating system, one of the best ways to catch malicious activity is through process tree analysis. On macOS, my personal favorite tool to use is TrueTree. This is open source and free and written by yours truly. I designed this tool because on macOS, the process tree tends to be very, very linear. By that, I mean due to XPC nature and inter-process communication, almost all processes on the system end up getting created from launch D. If you double click a program on the desktop, launch D creates it. If you open something through a plist, launch D creates it. What I aim to do with TrueTree was provide a process tree that's far more helpful for incident response analysts instead of the plain normal tree you'll get with some other tools. So here in the TrueTree output, we see that the system_update.plist ran update.sh, which created a bash instance, which created another bash instance, which created then a Python instance. Now we know because we've looked that this Python instance is the reverse shell. What we didn't see any signs of was the find command being executed inside that Python script. What this likely means is that an attacker is currently hands-on keyboard running the find command. This could be to find some vulnerability he knows exists, or more likely, using it to find documents that he can exfil on the system. So this is very bad, and we've gotten a little bit lucky here because you're not generally going to run an incident response script like this and find that you were running the script while the attacker was on the system. Usually it's a before or after thing. So we got a little bit lucky here, and this won't happen every time, but we definitely know that we want to get this off the system as soon as possible. Also in the TrueTree output, we see system_updater.app that we've confirmed is malicious being spawned by Core Services UI agent. Now Core Services UI agent is an Apple signed process who has many different tasks, one of which is to supply prompts to the user, and then act on those prompts based on what the user clicked. So because we know some of the background of what happened here, we can make the assumption that Safari threw a prompt once it tried to load the custom URL service. When it tries to load the custom URL, it says, Safari is trying to open system_updater.app. Do you want to allow this? When the user clicks allow, we end up with a process tree that looks like this. Again, this is kind of information we already knew, but it never hurts to have the same incident response information in the same in two different places. It lets us either catch it if we missed it the first time, or just reconfirm if we're seeing this for the second time. Now there's an additional step we're able to take here, and this is kind of optional, but that is if we want to really take a look at what happened and really get a good idea of what happened at the infection time, we can go to the website and see what that website is serving up. This is something you obviously want to do from a VM, maybe over a proxy. You want to make sure you're safe when you do this so you don't infect your host system. But in this case, we do want to go check it out. So we go to the IP address on the correct port, and we are actually brought to this website that just says downloading system update. If we take a look at the source code of this website, we see that when the user browses to the main page, they are instantly redirected to a link of systemupdater.zip. That means Safari or whatever browser you're in is automatically going to download a zip file that this website is serving up. After it's downloaded, there's a set timeout where it waits 7 seconds, which is more than enough time for the operating system to unzip it and register the custom URL scheme. So it's going to wait 7 seconds, and then it's going to redirect the user to the custom URL scheme, which then recommends that the application will be opened. So no 0 days used here or anything super in-depth, but it is still, we've gained the perfect understanding of what actually took place when the user came to this website, and that's pretty cool. Now, since this is a test scenario, I really like to show off how this attack actually occurred, since we're kind of in a unique position to see both sides. So let's take a look at how this actually looked from the attacker's side and the victim's side at the time it occurred. The first thing we'll see is that the attacker creates a shell, he starts a listener, and he basically is just going to sit there with Netcat and wait for the connection to come back to his system from the victim computer. He also sends an email that gets to the victim system. We see that it's a very vague email, and the details are very lacking. Someone should not really fall for this, but it happens all the time. So ultimately, he's just trying to get a user to click on a link, and when that user does click on the link, they are brought to a website. The website that we're familiar with at this point and that we have seen before. Now, keep in mind, we did not really see any signs that mail.app was involved in this attack. That is findable on the system. It sometimes can be possible to make that link, usually with something like TrueTree or process analysis. It's not always a guarantee, but it is possible. But that's getting a little more complicated and maybe best saved for another talk. Ultimately, we see that the app was downloaded and the browser waits till finally it's given an allow prompt, and the user is asked if they want to open this. Now keep in mind there'll be an additional prompt here if this isn't signed and notarized, and Apple will block it, but just for the sake of demoing, we have disabled Gatekeeper. But signed malware has made it through before. It certainly is getting harder with the new notarization requirements added, but this is an attack scenario that has been used in the past by different attacker groups. Meanwhile, back on the attacker's system, we receive a connection from the victim. The attacker goes and runs the whoami command, probably among many other commands that they're going to execute. All we know is at some point the attacker also executes the find command. So cleanup and remediation is actually going to be pretty easy on our end. First, we're going to unload the launch agent, which is going to kill the Python-based backdoor, and then we will delete the launch agent so it can't be run again at startup. Next, we'll delete the malicious shell script and delete the dropper application. Now, this was pretty easy for us in our case because the attacker did not gain root and they did not drop additional malware, like something that might happen a lot of times. You'll also notice we've left some analysis still open, which is what files might have actually been taken, but that's probably best saved for another talk. So today we reviewed a basic intrusion where we went over some of the items that Jamf Protect is collecting, as well as some of the manual collection and analysis of different artifacts. Malware and hands-on intrusions can get more complicated than this, and sometimes they can get even easier than this. But it's important to practice reviewing the data and making sense of it so that when something serious turns up, you have the experience and knowledge of knowing what you're looking at. Thank you everybody for attending this talk. Stay safe, and we will see you next time.